Hi class, welcome to this new video on tutorial 8, where together we're going to solve question 4. Now you have matrix A given, find the determinant of A minus lambda I, and then find the corresponding eigenvalue. Compare the sum of the eigenvalue with the trace of A, compare the product of the eigenvalue of A with the determinant of A, find the eigenvector or the corresponding eigenvalues, and write down the eigenspace of A. And then finally, explain why A is diagonalizable, and then write down the matrix P and the diagonal matrix P. Now, to answer such a question, let's start by recalling what we said in the lecture video, that to find the eigenvalues of a matrix, we need to solve the equation determinant of A minus lambda I equals to 0. So it means that what we have is a 7 minus lambda minus 1 minus 2 minus 1 7 minus lambda 2 minus 2 2 10. Now I can do what I see is that I can keep this as my pivot, right? And then I can work out to have 0 here and 0 over here. So what am I going to do? I will do that R1 is equals to R1 plus 7 minus lambda R2, right? To have a 0 in this first row. And then I'll also have that R3, right? Equals to R3 minus 2 R2. And this will give me the corresponding determinant here below. I'll have minus 1 plus 7 minus lambda squared. I'll have minus 1. I'll have 7 minus lambda. I'll have 2. And then I will have a minus 2 plus 2, 7, sorry, plus 2, 7 minus lambda. And then I'll have 0. Then 2 minus 2, 7 minus lambda. Then 10 minus lambda minus 4. Okay, I have that. So this can be simplified, right? I can simplify this by putting that 0. Then I do the multiplication here, right? Then this will give me lambda squared minus 14 lambda plus 48, right? And then I will have minus 1, 7 minus lambda, 0 minus 12 plus 2 lambda. Then I will have 12 minus 2 lambda, 2, 6 minus lambda. So right here you can see that I can do therefore the expansion. I can do the expansion with the first column. So this will be my pivot. So I will have this right. I will have this and this. So this will give me lambda squared minus 14 lambda plus 48, right? Minus 12 plus 2 lambda, 12 minus 2 lambda, 6 minus lambda. So I can do the multiplication, the determinant, 6 minus lambda, right? Lambda squared minus 14 plus 48 minus 12 minus 2 lambda and minus 12 plus 2 lambda, right? And then this will be equal to, I can see that if I do, okay, if I put 2 in factor, I can have, yes. So from here, you can see that from here, if I put 2 here, if I put 2 out here, it will give me 6 minus lambda, right? So I can factorize this term and this term, right? Okay, so this will give me 6 minus lambda times lambda squared minus 18 lambda plus 72, right? So, and this therefore will give me 6 minus lambda, lambda minus 6, lambda minus 12, right? So what I did is that I factorized this term. Okay, so having done this, I can therefore find the eigenvalues by setting that delta lambda I equal to 0, which means that I have lambda equal to 6 and 6, and and lambda equals to 12. So lambda equals to 6 has a multiplicity of 2 because 6 comes 2 times, right? Now, the next question was to compare the sum of the eigenvalue, compare, right? So what do we see? The sum of the eigenvalue is 6 plus 6 plus 12, which equals to 24. And if we look at our matrix A, right, 7 minus 1 minus 2 minus 1, 7, 2 minus 2 to 10. If we find the trace of A, we have that is 7 plus 10 equals to 24. The trace of A is the element, the sum of the element of the diagonal of the matrix. So they are equal to each other. Now, the third question is compare the sum, compare the product. So we saw that the product of lambda is 6 times 6, right? You have 6 times 6 times 6 times 6 times 12, right? Which is for the 2. And then this is A. You realize that if you find the determinant of A using any other method that we explored before, it will give you 3, it will give you 432, right? So you realize that the product of the eigen values is also equal to the determinant of A. Now the big question is find the eigenvalue, the eigenvector, sorry, of A. Now, to find the eigenvectors of A, we need to always solve the equation A minus lambda IV equals to 0. Now, let's look for the case of lambda equals to 6. So I will have that A minus 6IV equals to 0, leading to the augmented matrix 1 minus 1 minus 2, right? Minus 1, 1, 2, minus 2, 2, 4, right? So I have this. I can do that R2 equal to R1 plus R2, and then R3 equal to R3 plus 2R1. This will lead me to 1 minus 1 minus 2, yes, and then 0, 0, 0, 0, 0, 0, right? Now, I can see that this is fixed and these two are free. So I will have that x2 equals to s and x3 equals to t. So from the first row here, I have that x1 equals to x2 plus 2x3, which equals to s plus 2t, right? So my solution, the vector here, or the, yes, so my solution here of x will be s plus 2t plus s plus t, which equals to s110 plus t201. S and t are scalar. So you see, we we then have two vectors. You can see we then have two vectors, and this makes much sense because for lambda equals to 6, the multiplicity is 2, right? And then we have two distinct eigenvectors, and this will be useful to give a conclusion about all these studies, as you will see. And then for lambda equals to 12, we then have our augmented matrix when we apply this applying this equation over here. We have our augmented matrix, which will be minus 5, minus 1, minus 2, minus 1, minus 5, 2, minus 2, 2, minus 2, right? So if you do that, R2 equal to R2 minus 5 R1, right? Yes, and you do R3 equal to R3 minus 2 R1. Yes, you will have minus 1. So yeah, so sorry, to have this here, I've swapped R1 with R2 so that I can have this as a pivot in the on the first row. So this gives me minus 1, 5, 2, and 0, 24, minus 12, minus 12, and then here I have 0, I have 12, I have minus 6. And then you can see that this also here, here if I can therefore divide this by 12 and divide this by 6, right? And this will give me minus 152, 0, 2, minus 1, 0, 2, minus 1, right? So I will then do that R3 is R2 minus R3. It will give me minus 152, 0, 2, minus 1, 0, 0, 0. Right. So from here I can quickly see that this is a fixed variable, and then the third variable will be free, right? So from the second row, so I'll have x3 equals to s, and from s, and from the second row, I will have that x2 equals to 2x2 equals to x3, which is s. So I will have that for my solution, x1, x2, x3. I will have that that x1 equals to minus s over 2, x2 equals to s over 2, and x3 equals to s. So having this is minus half, half and 1, right? And again, this can be rewritten if I multiply everything by 2, by minus 1, 1, 2. And then s is any scalar. So for lambda equals to 6, we have two eigen vector. We have 1, 1, 0, and we have 2, 0, 1. And for lambda equals to 12, we have the eigenvector v3 equal to minus 1, 1, 2. So therefore, the corresponding eigenspace for lambda equals to 6 equals to the vectors expressed as follows. So we have a 2, 0, 1. We have alpha, beta equals to r. So don't get confused. If you see that here we use s and t, and here we use alpha and beta. These are essentially similar because they are scalar. And I have this 12 equals to alpha minus 1, 1, 2, and alpha is a scalar. Now we have found the corresponding eigenvectors and we have written down the eigenspace. Now the question is the last question is will now be to explain why A is diagonalizable. So we can say that so that why A is diagonalizable. So we can say that since we have right a 3 times 3 matrix, right, with 3 independent eigenvectors, right? Then A is diagonalizable. So we also saw the fact that for lambda equal to 6, we have multiplication of 2, and then from here also we also have a 2 distinct eigenvectors, right? This also makes also we had 2 distinct eigenvectors, and which is a significant argument also to use when it comes to diagonalizable matrix. Now the last question was to write P. So we see that P, we know that matrix P is a matrix of the eigenvectors of A. So this is the first, this is the second, and this is the third. I will know that D is a matrix of the eigenvalues. So yeah, so we have that. Thank you very much, guys, for your kind attention. See you soon in the next video.